Welcome to 10th class math classes. In this video, we will learn tangents and secants, okay, from the Telangana class 10 maths book. This is the chapter 9 of the maths book. We'll learn introduction, line and a curve, tangents, number of tangents to a circle, construction of tangent to a circle from external point, segment of circle formed by the secant, finding area of the segment, and some exercises. Okay. It's a simple chapter. We have very few theorems to learn actually. It's all about more about practice actually. Let's get into the chapter. Introduction. Okay. We have seen before in the two line equations. Okay. Two lines can either intersect each other, they can be parallel or they can be coincident. Right. So what if one of the line is a curve? Okay. Then what are the options you have? Okay. So if you have a curve and a line or a circle and a line, basically curve is a part of the circle, right? You have three options. Either the line intersects the circle or it doesn't intersect. That is the first option. It intersects at 2 points or it intersects at the only 1 point. It touches the circle at 1 point. Okay, these are the three options you have with the circle and a line. Correct? So out of this, uh, here there is no interaction. Basically, line and circle both are independent. Okay, here AB is called in the image 2, we call AB is called a secant. Okay, it is intersecting the circle at 2 points. It is cutting a sector basically, right? It is making a sector. Okay, and the AB, this part of the circle is called a segment. We call this as a segment, and AOB with the curve, with the circle curve, is called a sector, right? And in the third diagram, basically, circle is touching the line at only 1 point. Circle is touching the line PQ only at 1 point, that is A. Okay, this is called a tangent. Okay, this is called a tangent to a circle. Okay, tangent to a circle touches the circle at only 1 point. Okay, that is the definition of a tangent. And secant touches the circle at 2 points. Okay, and do you have more points? Can a line touch a circle at more than 2 points? Definitely not, right? So these are the two options what we have. So one is called tangent, other one is the secant. Okay, now, okay. So here AB we call it a chord, right? AB is a chord and AB, this part is a secant. Okay. Now draw a circle with any radius, draw four tangents at different points. How many more tangents you can draw to a circle? Okay, this is the one question. Okay, think about it. How many tangents you can draw in a circle? Okay, circle is basically a union of infinite points. Okay, at equidistance from the center. Correct. The distance is what we call radius. So there are infinite points, and every point you can draw a tangent. Correct. So there can be a infinite tangents on a circle. Okay. How many tangents can you draw to a circle from a point away from it? Okay, you can try it yourself. Okay, you take a circle, put a point outside the circle somewhere and try to draw tangents. How many you can draw? You can draw basically two. Okay, two tangents you can draw from an external point. Okay, in the adjacent figure, which lines are tangents to the circle? Okay, let's see. M is a tangent, this is a tangent, it is touching at 1 point. P is a tangent, it is touching at 1 point. Okay, L is not a, L is a secant basically, right? L is a secant and Q is a secant. Okay. So the activity mentioned here is fairly simple. You can do it yourself. You can go through it. Okay. Okay. When you have a tangent, it touches the circle at 1 point. Correct. That is called point of contact. Point of contact. Okay. And at point of contact is the point where the line or tangent touches the circle. Okay, and the point where it touches, it actually makes 90 degrees with the radius. Okay, we will prove this one. This is 90 degrees to the 90 degree at this radius is 90 degrees to the tangent. Okay, so let's prove that. How we can do that? The theorem 9.1 says basically tangent at a point of a circle is perpendicular to the radius to the point of contact. Okay, so xy is the tangent, it is touching the circle at P, so OP is perpendicular to xy. This is what we should prove. Correct? So this is very simple. Let's assume that there is another point on the line, let's say Q. Okay, another point on the line which is Q. Okay, which is perpendicular to the line xy. Let's assume. Okay, we are proving it by negation. Okay, now OQ, let's assume that OQ is perpendicular to xy. Okay, but what is the length of OQ? OQ and OP, which is bigger? OQ and OP. OQ is outside the circle. P is the only point which is on the circle, right? And line intersecting. There is no other point where line and circle are intersecting. Correct? P is the only point. So Q is another point on the line which is outside the circle. So obviously, OQ will be greater than OP. Correct? OQ will be greater than OP. But what we have learned, a point and a line if you given, only the perpendicular line from the point to the line is the smallest distance. Correct? Shortest distance from a point to a line is the perpendicular line. Correct? Which means OP is the shortest distance here, not OQ. Correct? That implies OP is perpendicular to XY. Right? There cannot be any other point which is perpendicular to XY. OP is nothing but radius, so radius is perpendicular to the tangent. Okay, and just to note actually, the line containing the radius through the point of contact is called the normal to the circle at the point. Okay, this is called point of contact is called normal. The line containing the radius through the point of contact, that is OP. OP is called normal here. Okay, OP is called normal. Normal is perpendicular to the tangent. Basically. Okay, now how can you prove the reverse of the above theorem? It's very easy. You can try it yourself. Okay, now how do we construct a tangent to a circle? Okay, this is easy. You take any point on a circle, okay, and draw the radius. You know the center of the circle, you draw the radius, and you draw a line at 90 degrees to that on the uh, point where the on the uh, uh, point on circle. Okay, take the point on circle, draw the radius, and draw a perpendicular line to the radius. That is nothing but tangent at that point, right? So this is as simple as that. Okay. Now, how can you draw a tangent to a circle at a given point when the center of the circle is unknown? When the center of the circle is unknown. Okay. So this is one thing we should try. Draw a circle. Take any point on the circle. Okay. Any point on that circle. Draw a line. Okay. And draw a line and draw a secant or chord basically, QP chord. Okay. The line XY and QP meets at P on the circle. Okay. Now, now how do you prove that this is a tangent? Okay. You measure the angle here, XPQ, and take any point on the circle R, and QRP will be same. Okay. Then it is a tangent. Okay. We will learn about this theorem later. Finding length of the tangent. Okay, can we find length of the tangent PA to a circle from a given point? Okay, so this is easy. You have a circle, O is the center. Okay, radius is 6, it is given. Okay, and A is the point on circle. Okay, OA is the normal. OA is the radius basically. Okay, and from P there is a tangent AP to the circle. Now we need to find either length of AP or OP. Okay, now it is given that OP is 10. Okay, the point is 10 centimeters away from circle center. Now we know that it forms a right angle triangle. PAO is a right angle triangle at 90 degrees at A, correct? And the radius is 6, hypotenuse is 10. So AP is nothing but 10 square minus 6 square, square root of it, which is nothing but 8 centimeters. Okay, so this is very easy. Okay, now let's do the exercise part 9.1. Okay, a tangent to a circle touches it in how many points? 1 point. Correct? That's what is the definition of a tangent. Line intersecting a circle in 2 points is called a secant. Correct? Called. Maximum number of tangents can be drawn to a circle parallel to the given tangent. Okay, how many? You have a tangent to a circle. How many more tangents you can draw which are parallel to the given tangent? Okay, you can draw just one more. And where that will be? Exactly diagonally opposite point you take. Okay, on the circle, you have a you have a tangent at point P. Okay, so you take the diagonally opposite point to the P and then draw a tangent there. These two tangents are parallel. How can you prove that? Both the diagonal makes 90 degrees with both these tangents, correct? At the two ends. Okay, that means the angles are same, so they are parallel. Okay, so you can have only one more line which is parallel to the given tangent. Only two tangents at any point will be parallel in a circle. Okay, like that there can be many pairs of tangents, okay, which can be parallel because circle is made up of infinite points, right? So all infinite, every point on a circle will have another parallel tangent. Now the common point of a tangent to a circle and the circle is called normal. Okay, this common point is called a normal. We can draw infinite tangents to a given circle. Okay, the circle can have infinite parallel tangents at the most, infinite parallel tangents, but all are not parallel. Only two are parallel at any point. Okay, two are parallel to each other, but like that you can have infinite parallel tangents. Okay, a tangent PQ at a point P of a circle of radius of 5 centimeter meets the lines with the center O at a point Q, so that OQ equal to 13 centimeters. Find the length PQ. Okay, draw the picture correctly. You have a circle with center O. Okay, there is a tangent PQ. Okay, tangent at P on the circle. Okay, and it is given that OQ equal to 13. Okay, and OP we know radius of the circle which is 5 centimeters. So they are asking what is the value of PQ. Very simple. It's very clearly shown in the diagram that this is a right angle triangle. Correct. So PQ square equal to 13 square minus 5 square, which is nothing but 144. So PQ is 12. Okay. Next, draw a circle and two lines parallel to given line drawn outside the circle such that one is a tangent and other is a secant of a secant to the circle. So you can clearly see, right? One is tangent, other one is a secant, both are parallel lines. Okay, it's very simple. Calculate the length of the tangent from a point 15 centimeters away from the center of a circle of radius 9 centimeters. Okay, okay, you have a circle basically with center O, then radius is 9. Okay, and then you draw a perpendicular line to the radius here. Okay, PQ, and you can cut it from center at 15 centimeters. This, this is nothing but Q. Okay, you will draw it like this. Now PQ will be 12 centimeters by calculation, 15 square minus 9 square, which is 12. Fifth, prove that the tangents to a circle at the end points of a diameter are parallel. This is very easy. Uh, So you have circle, you have a diameter, two tangents are drawn. You have 90 degrees here, 90 degrees here, which tells us these angles are same. Those this is a transverse, and these two are parallel lines. Right? That's very simple. Okay. So yeah, let's go next. Number of tangents to a circle from any point. Okay. We already know that we can draw two tangents from a given point outside the circle to the uh, circle, right? One given point outside the circle, you can draw two tangents to the circle. Okay, just a simple activity. You take a point inside the circle, definitely you cannot draw any tangents, so you will get only secants. Okay, if the point is on the circle, you can draw one tangent because one point, one tangent. If the point is external to the circle, you can draw two tangents like this. Okay, so this is the observation which is given. Now let's see some more theorems related to tangents. The length of tangents drawn from the external point to a circle are equal. Okay, this is very important to note down. Very basic theorem. Okay, from P there are two tangents drawn. You have to prove that AP equal to BP. AP equal to BP. This is what you have to prove. And we know that radius makes 90 degrees to the uh, tangent. Okay, so you have two triangles here. What are the two triangles? OPA and OBP. Okay, OAP, OBP. These are the two triangles. If you see, both are congruent. How? These two sides are same radius. Both are radius. You have 90 degrees. You have another common side. Correct? You have another common side. So since two sides are same and one angle is same, SAS. Okay. From SAS, you can prove that uh, these two triangles are congruent. Since they are congruent, AP should be equal to BP. Okay. So this is very simple. Um, next, you can use Pythagoras theorem to prove also because you have radius common and uh, OP is common. Obviously, AP will be OP square minus OA square root of basically square root of OP square minus OA square, which is also same as OP square root of OP square minus OB square. Correct? So we can prove that way also using Pythagoras theorem because these two are right angle triangles. Construction of a tangent to a circle from external point. How to do this? This is one way is given here. Let's take a point P outside the circle. First, join PO. Okay, O is the center of the circle. Join it. Find the midpoint using you know right how to find the midpoint. You can cut with the more than 50% of the size you take length. Then cut it both sides. From then you get if you join this, you will get the midpoint M. Okay. Now using midpoint M, okay, draw a circle with MP or MO as radius. Okay. This will cut the original circle at 2 points, A and B. Okay. Now from this point P, you can draw two tangents, PA and PB. They will touch at only 1 point. Okay. How do you prove it? It's very easy. It's very easy to prove. You have, if you join OA, okay, if you join OA, this is a right angle triangle. Correct? If you join OA, it's a right angle triangle. And OA and OB, if you join, okay, PA is perpendicular to OA because it is an angle in a semicircle. If you see this bigger circle, if you see the bigger circle, PO is the diagonal, correct? PO is the diagonal. Diagonal always makes 90 degrees on the circle. So A is a point on the bigger circle and angle PAO will be 90 degrees, which means in the small circle, PA is the tangent which is making 90 degrees to the OA line OA radius. So that is the tangent, right? So this is how we can prove it easily. Another statement here, the center of a circle lies on the bisector of the angle between two tangents drawn from the point outside. Okay, so yeah, this is also easy to prove actually. You have you can take same congruency principle here, triangle congruency. You have a P point outside the circle. You draw two tangents. Okay, so obviously you get two right angle triangles. Okay, the two right angle triangles here are one is OQ radius, OR radius, both are same. This is the common side which is same, correct? And you have 190 degrees, okay, which is same. Okay, we also know that QP, PQ equal to PR, which is same. So side, angle, side, these two triangles are congruent. Okay. Now you have a these two triangles are congruent means these two angles here are same, equal, which means OP divides the angle P. At P, whatever is the total angle formed, OP divides it because these two are same, equal angles. Okay. Now another statement, in two concentric circles, the chord of the bigger circle that touches the smaller circle is bisected at the point of contact with the smaller circle. This is also very easy to prove. You have a circle inside small circle, okay, C2, and bigger circle C1, same center, both are concentric circles, so same center. And you have a line AB which is a tangent to a smaller circle C2, okay, at the point P. OP is the normal. OP is the normal. So this is 90 degrees. Now again we can easily prove from congruency, correct? We can prove very easily with the congruency. This is a common side for both the triangles OPA and OPB. OP is common, okay? And this is a equilateral triangle, sorry, isosceles triangle. OA equal to OB, correct? So these angles, angle at A and angle at B are same. Yes, okay. And this is the bigger radius. This is also same. We know OA and OB also radius of the circle C1. So these two also same. Okay. From all this data, we can easily prove that these two triangles are congruent, which means AP equal to PB, which means P divides AB into two equal parts. It bisects basically. Okay. Now another statement. If two tangents AP and AQ are drawn to a circle with center O from an external point A, okay, angle QAP, that is theta here, is equal to twice of these two angles, twice of this angle or twice of this angle, okay, OPQ or OQP. How to prove this? Okay, yeah, this is also easy. You draw a line here, or okay, other way to do is you see the triangle APQ. APQ is the isosceles triangle because AP equal to AQ. So angle here P equal to Q, both are same, correct? And sum of these three angles is 180 degrees. That is APQ plus PQA plus QAP is 180 degrees. But these two angles are same. Okay. So one of each of that angle is half of 180 minus theta. That is 90 minus theta by 2. Correct? Each one is 90 minus theta by 2. Now we know that this complete angle is 90 degrees. Correct? Angle OPA is 90 degrees. Out of that, QPA is 90 minus theta by 2. So obviously, OPQ is theta by 2. Similarly, this is also theta by 2. So these two angles are theta by 2. If the angle made at the external point A by two tangents to a circle is theta, then these two angles will be theta by 2. Okay. It's another one. Now, this is another simple statement. If a quadrilateral ABCD is drawn to circumscribe a circle, then AB plus CD equal to BC plus DA. Okay, which means sum of opposite sides are equal. That's what the statement is. Okay, so this is also easy. Sum of opposite sides is equal. Okay, AB plus CD equal to BC plus DA. Okay, so how can we do this? Okay, dr and ds are equal. Dr and ds are equal because these are the tangents drawn from point D to the circle. Okay. Similarly, cr and cq are same because these are the tangents drawn from C. Okay. bq equal to bp. AP equal to AS. Now, if you sum them up, okay, AP plus BP, okay, equal to AP plus BP and DR plus RC equal to these two this side. So they all will be equal because we have all equal sides. These are two pairs of equal lines we have actually. Okay, with that we can very easily prove it. Mm. Yeah, let's do an example. Draw a pair of tangents to a circle of radius 5 centimeters with which are inclined to each other at an angle of 60 degrees. Okay. So there are ways to draw. First, let's draw a rough diagram and then we can draw it how we can exactly draw. Okay. So this is 5 centimeters radius. We know circle is 5 centimeters radius. There is a point P. Two tangents are there. Okay. This is 60 degrees. We know this is 60 degrees. Okay. So if you find OP, if you find the OP distance, then we can easily draw tangents. Correct. We need to find OP. This is 5. This is 60 degrees. Okay. So this the small angle will be 30 degrees. Correct. Small angle is 30 degrees in the triangle OPA in the or OAP. Sine 30 degrees is opposite by hypotenuse, which is OA by OP. Correct. OA is nothing but 5 centimeters. So 5 by OP equal to half. OP equal to 10 centimeters. Now we know that OP is 10 centimeters. Once you know the OP, we already seen how to draw two tangents from the external points. So draw first circle with 5 centimeters radius, then take from the center 10 centimeters line, draw another circle with the center at the tangent at the point of circle. Okay, draw another circle. It will touch 2 points AB. From this P, you can draw two tangents now. This is how we will draw. Once you know OP, it is very easy to draw. Okay. Now he's asking us to try this above construction with another method, which is given here. Let's do that. Okay. Draw a pair of radii OA and OB. Okay. OA and OB we draw such that angle BOA is 120 degrees. This is 120 degrees. Okay. Draw bisector of BOA. Okay, draw bisector of BOA. Okay, and draw lines perpendicular to OA and OB. At OB and OA, draw perpendicular lines. These perpendicular lines will go and touch the center line OP at P. Okay, now it's telling at P. Now, if you measure this angle, it will be 60 degrees. Okay, we have seen this already because if you draw one line here, this small angles will be theta by 2 and theta by 2. If this is 60, 30 and 30, 60, correct? Total angle should be 180. So 180 minus 60 is 120 degrees. So we know that if you want to have a 120 degrees here, okay, at the center, the card will subtend an angle of 120 degrees. That if you know, you can draw it very easily. This is the other way. Okay. Let's do exercise 9.2. Choose the correct answer and give justification for each. Okay, the angle between the tangent to a circle and the radius drawn at the point. Okay, we know that this is 90 degrees. Both are perpendicular. Right? It's called a normal. Right? Next. From a point Q, the length of the tangent to a circle is 24 centimeters and the distance of Q from the center is 25. The radius of the circle is. Okay, we know that this forms a right angle triangle. Okay, hypotenuse is 25 and one of the side is 24. So radius is what they are asking. Okay, which is nothing but 25 square minus 24 square, which is 49. Okay, so square root of 49 is radius, that is 7 centimeters. This is the answer. Okay, A. Next. Yeah, next. In the adjacent figure, AP and AQ are the two tangents to a circle with center O. Okay, and the angle made at center, that is POQ, is 110 degrees. What is the angle at PAQ? That's the question. So we know that these opposite angles, sum of these opposite angles is 180 degrees. So angle PAQ will be 180 minus 110, which is 70 degrees. Okay, that's the answer. Next. In the adjacent figure, PA and PP are the tangents to the P. Okay, this is exactly the reverse question which is asked. He has given angle at the P, okay, which is 80 degrees, and he is asking half of this angle. Okay, half of the angle made at the center. So we know that this is, if this is 80 degrees, the angle made at center will be 100 degrees. The total angle is, and half of it, that is angle POA will be half of it, which is 50 degrees. Okay, next. In the figure, xy and x dash y dash are two parallel tangents to a circle with the center O and another tangent AB with the point of contact C intersecting xy at A and x dash y dash at B, then angle BOA. Okay, this is the angle is asking. How much this angle? Okay. Yeah, we can easily tell it is 90 degrees, but let's prove it. Okay. We know that A is a point external to the circle and two tangents are drawn here. Okay. Now OA is the line from the center, correct? Center of the circle. So OA will divide these two angles into equal parts. So 45 degrees and 45 degrees. So angle here is angle OAB is 45 degrees. Similarly, angle OBA also 45 degrees. 45, 45, 90 degrees. So here it will be 90 degrees. Remaining angle in the triangle is 180 minus 90, which is 90 degrees. Okay, next. Yeah, second question. Two concentric circles of radii 5 centimeters and 3 centimeters are drawn. Find the length of the chord of the larger circle which touches the smaller circle. Okay, we need to find BC. Okay, length of the chord of the larger circle, that is BC, which touches the smaller circle. Okay, these two are given. Now this is very easy. AB is equal to AC, we know. Okay, so this is the right angle triangle. Correct? So if this is 5, this is 3, obviously AB equal to 5 square root of 5 square minus 3 square, which is 4. Okay, if AB is 4, AC is also 4, so BC is 4 plus 4, that is 8 centimeters. Okay, correct? Okay, AB equal to 4 centimeters. Chord of the larger triangle is BC. BC equal to twice AB, which is 8 centimeters. Next, prove that the parallelogram circumscribing a circle is a rhombus. Okay, yeah, this is a good question. So if there is any parallelogram you take, if you circumscribe a circle inside that, it will be rhombus, means all four sides should be equal. This is the question. Okay, we have proved one statement we have seen before, that sum of opposite sides is equal to, that is AB plus CD equal to BC plus DA. Okay, if it is a parallelogram and the sides are different length, then it can never be, right? Is it possible anytime if you have a parallelogram with different length side, opposite sides, and the length and breadth are, if they are different size, okay? Is it possible that statement cannot be true, right? So if for that statement to be true, it has to be a rhombus. Only in rhombus you can circumscribe a circle. In parallelogram with different sides, you cannot circumscribe a circle. Okay, so I think proof is exactly same way what we seen in the statement. Okay, we'll just prove that all these sides are same pairs of sides, correct, and then sum them up. Okay, so we will get AB plus CD equal to BC plus AD, which is the proof which was given already, correct, which means AB equal to CD and BC equal to AD. Since AB equal to CD and BC equal to AD, okay, these two will be twice, right? So AB equal to BC, that means. Okay, next. A triangle ABC is drawn to circumscribe a circle of radius 3 centimeters, such that segments BD and DC, into which BC is divided by the point of contact D, are length 9 and 3 centimeters. Okay. So there is a triangle ABC. There is a circle circumscribed. Okay. And it is touching at side D. Okay. This is 9 centimeters. This is 3 centimeters. Okay. Find the sides AB and AC. Find the sides AB and AC. Okay. Okay. Let us populate the values. Okay. One thing is that if you look at the image, it looks like it is a right angle triangle. Then it is very easy to apply Pythagoras theorem and get the other values. Okay. But we will not do that. We will not do that because it is not given as right angle triangle. Okay. So we should not assume that it is a right angle triangle. So we will assume that it is not a right angle triangle and solve the problem. If it is given as right angle triangle, the solution is much easier. Okay. So if you see this is 9 centimeters, BE also will be 9 centimeters because it is a tangent from the same point. This will be 3 centimeters. These two will be X and X because tangents from A. Okay. Now these are the values we know. This is 3 centimeters given. So we know that this is OF also 3, OE also 3. Okay. AE equal to AF equal to X. We are assuming. Okay. Then from the area of ABC from Heron's formula is this one, right? Square root of S into S minus A into S minus B into S minus C. So from this S equal to A plus B plus C by 2, which is nothing but 12 plus X. Okay. So this is equation 1 for us, area of triangle. And the other way is area of triangle is area of ABC equal to OBC plus OAC plus OA. Okay. OBC, this is one triangle. Okay. Then AOB, this is other part. This is other part. Three parts we are making, and each one has a height here, right? Because this radius makes 90 degrees with the line, so this is the altitude of this triangle, correct? So each one will take 12 into 3 by 2, this area. This is 9 plus x into 3 by 2, 3 plus x into 3 by 2. So if you sum up all these things, what you will get is 36 plus 3x. Okay. Now these two are equate, right? Once you equate them, we know that 27 into 12 plus x equal to 3x plus 36 whole square. Okay. Now take the 3 out or 9 out basically. If you take 3 square out, 9. 9 if you divide, you will get 3 times this one. Okay. So this is the final equation what you will get. X equal to minus 12 or 6. This is what we'll get. Okay. The length cannot be negative. So x is equal to 6. So this will be 6. So 9 plus 6 is 15. 3 plus 6 is 9. 15 and 9 are the AB and AC. Okay. Next. Draw a circle of radius 6 centimeters from a point 10 centimeters away from its center. Okay. Construct a pair of tangents to the circle and measure their lengths. Verify using Pythagoras theorem. Okay. This is a uh, construction problem. I think you can do it yourself very easy. Okay. Uh, how do you verify it? It will form a right angle triangle. So you measure the length of AC, which will come 8 centimeters. Okay. Next. So this is how it will look basically. You have a circle, radius 6 and 6. You draw. How do you draw basically? You draw a line from O, 10 centimeters, and then take it 5 centimeters. You draw a circle. It will touch at 2 points. Those are the tangential. Okay. So once you measure it, you will get same. Construct a tangent to a circle of radius 4 centimeters from a point on the concentric circle of radius 6 centimeters and measure its length. Also verify the actual method. Okay. So this is what is telling. You have a two concentric circles. Okay. OA equal to 4 centimeters. OB equal to 6 centimeters. Okay. Construct a uh, tangent from this. BA is the tangent. Okay, BA is the tangent. Okay. Now AOB is a rectangle triangle. AOB, AOB is a right angle triangle. Okay. Because it is a tangent, it will form a 90 degrees with the radius. Correct. So OB square equal to AB square plus OA square. OA square we know, OB square we know. We just need AB value. So AB square equal to 6 square minus 4 square, which is 20. So AB equal to square root of 20. This is the measurement you will get. Okay. Next. The next problem. In a right angle triangle ABC, a circle with side AB as diameter is drawn to intersect with the hypotenuse in P. Prove that the tangent to the circle at P bisects the side BC. Okay. So first, let's see the diagram. Okay, this is the diagram here. You have a triangle ABC here, ABC. Okay, it's a right angle triangle, right angle at B. Okay, and there is a circle drawn with O as center. Okay, which is O is the midpoint of AB. Okay, A is basically AB is the diameter of this circle. Okay, it intersects AC at P, and there is a tangent drawn. There is a tangent drawn at P. Okay. Now the question is PQ bisects BC. That means BQ equal to QC. This is what you have to prove. Okay. Now look at the tangents to this one. There is a tangent from here from Q. There are two tangents drawn to this circle, QP and BQ. Right? QP equal to BQ because this is the tangents from the same point. Okay. Correct. These two are same. And also APB equal to 90 degrees. APB equal to 90 degrees. How? Why this is 90 degrees? This is the angle subtended by the diameter in the semicircle, correct? Angle in the semicircle, which is 90 degrees. So if this is 90 degrees, we know that other side also is 90 degrees. Okay. If this is 90 degrees, okay, this is X, this will be Y, these two will be same. Okay. Now let's see. Next. Angle BPC is also 90 degrees, which means PQ equal to PB. PQ equal to PB. Okay. This we know. With this, we can say that this angle here, okay, if this is X, this is also X. Okay. These two are X and X. Okay. Now, next. Angle BPC can be written as angle BPQ plus QPC. Correct? Sum of these two angles, angle BPC. Now, next. That implies QPC equal to 90 because this total is 90 degrees, we know. 90 minus BPQ. Okay. QPC is 90 minus BPQ. Okay. And BPQ is same as PBQ. Correct? Same as this angle. Correct? So 90 minus this angle is nothing but this angle, right? Because these two are 90 degrees. If this is 90 degrees, these two are 90 degrees. 90 minus this angle is nothing but this angle. So all are same basically. So PQ equal to QB as well as PQ equal to QC. Okay. From these two equations, we can derive that QB equal to QC, which means PQ bisects PC. Okay. So hope you understood this. Just go through this once again and do it yourself. There are multiple ways to do it. Okay, this is one of the way I have chosen. You can try it yourself. You can do it in multiple ways. You can also do it this way in triangle ABC. In triangle ABC, okay, this tangent is parallel to the diameter here because this is 90 degrees here. You will get another 90 degrees here. So you can prove that OPQB is a square. Okay, and this parallel, these are all parallel, right? Parallel lines, so it will bisects into equal parts here. Ratios will be same. So that way also you can try actually. Okay, another way. Okay, next. Okay, let's go to the segment of a circle formed by a secant. Okay, now this is a circle and AB is a chord or secant. Correct. Now this is the area. Uh, this basically cuts the circle into two areas segments. One is minor segment, other one is major segment. Correct? So, if you look at these pictures, how do you calculate the area of this one? How many pictures are involved here? You have a square, and rectangle here. You have a rectangle and circle here. Similarly, you have different. Okay. So in this one, how many figures are there? You have a square here, correct? You have a semicircle here, semicircle, semicircle, semicircle. Okay, square and four semicircles are there. Here you have a quarter circle and a triangle. Quarter circle and a triangle. So this is the area. How to calculate this, we will come to know. We'll go next, and just to refresh yourself, get to know areas of each figure. Okay, rectangle it is length into breadth, square it is uh, side square. For a triangle, it is half into breadth into height. Okay. For circle, it is pi r square, where r is the radius. Okay. Now, if a line uh, cuts the circle and the segment is formed, you have two segments, minor segment and major segment. Correct. In a semicircle, both segments are equal. Correct. So, how to find areas of these? Okay. One way of finding this area of this one is, you know, the sector area. Okay. Okay. A OAPB is a sector, correct? Complete this one is a sector. And minus triangle area, if I do, I get the segment area, correct? So how do you find the sector area? If you know the angle, how much is the angle here? Okay. The angle by theta, if this is theta, theta by 360 degrees into pi r square. Theta by 360 degrees into pi r square is this complete sector area, correct? Once you know the complete sector area, you calculate this triangle area and subtract. Then what you will get is this shaded area, correct? So that is the one way. That is what is shown here. Okay. X degrees by 360 into pi r square minus area of the triangle AOB or OAB. Okay. So this is one way. How do you find the area of major segment? You just pi r square is the area of circle, and subtract the minor segment, you will get r. You know that it is uh, x degrees, right? You can change this, okay? And I try to do easy ways. Find the minor segment area and subtract it. That's the best actually. Okay, next. Find the area of sector whose radius is 7 centimeters. Okay, with the given angle. Okay, let's not do the calculation, but I will tell you how to do this. Let's call this R. Okay, so this is 60 degrees. So 60 by 360, 60 by 360 into pi r square. That's the area of the sector. Correct? 30 by 360 into pi r square, 72 by 360 into pi r square, 90 by 360 into pi r square, 120 by 360 into pi r square. Right? That's the area. Calculate yourself. The length of minute hand of a clock is 14 centimeters. Let this be R. Find the area swept by the minute hand in 10 minutes. In 10 minutes, minute hand goes two numbers, right? From, let's say if it is at 12, it will go to 2, which means it is actually sweeping 2 out of 12 or 2 out of 12. Correct? That is 1 by 2 by 12 is 1/6. 1/6 area it is sweeping. So 1 by 6 into pi r square. That is the equation. If you want, you can calculate angle. Minute angle is how much? 360 by 60. That is 6 degrees. Okay. For 10 minutes, it will be 60 degrees. So 60 by 360. Correct? 60 degrees by 360, which is nothing but again 1 by 6 into pi r square. That's the value. Okay. Let's do some examples here. Find the area of the segment AYB. AYB. Okay. This is the sector. Okay. It's not shaded here, but this is the one. Okay. It is given that radius of the circle is 21 centimeters and AOB is 120 degrees. Okay. How to do is very easy. Okay. Once you know that it is 120 degrees, area of the sector area is 120 by 360 into pi r square. Okay. That is 462. Now, and now you have to subtract this triangle area. Correct. How do you do that? You need to find this perpendicular altitude, basically altitude of this triangle. How do you find it? You draw altitude from O to, let's say, let's call it D. Okay, let's call it D. Now we know that this will be 60 degrees here because it will bisect the angle also. Altitude in isosceles triangle will bisect the angle also, right? So the angle here is 60 degrees. Now you apply sine theta or cos theta to get the value of half of this. Okay, then that is the double of this. So you get the base and height, altitude, both you will get. From that you can calculate. Okay, so this is how it is 60 degrees. Okay, now if you call it M, midpoint M, then okay, sine 60 degrees or cos 60 degrees you can use, and you can get OM value as well as AM value. Okay, and AB is nothing but a double of AM, right? With that you can get the triangle area. Now area of the segment is basically subtraction of both the values 1 and 2. Okay, next. Find the area of the segment shaded in the figure if PQ equal to 24, PR equal to 7 centimeters. Okay. Now we know that this is the diameter, so it will subtend a right angle at P, correct? So this is the right angle triangle. So QR is nothing but square root of 24 square minus 7 square. So you will get 25. Okay, QR is nothing but 25. This is what you will get. And once you know this is 25, radius is half of it, right? 25 by 2. Now you take the semicircle area pi r square by 2, okay, and subtract the triangle area. Since it is a right angle triangle, it will be 24 into 7 by 2 is the area of the right angle triangle. So radius of the circle is half of cube, that is 25 by 2. Now area of semicircle is half pi r square, which is nothing but this value. And area of the triangle is 24 into 7 by 2, that is 84. Subtract both of them, you will get the value. Next. A round table top has 6 equal designs as shown in the figure. If the radius of the tabletop is 14 centimeters, find the cost of making the design with a paint at a rate of 5 rupees per centimeter square. Okay, so if you look at the diagram here, this shaded part is what we want to paint. So first we need to find the area of this shaded part. How do you find it? Area of the circle is pi r square, which is 616 centimeter square from the given data. And this is basically a hexagon, right? It's a hexagon, regular hexagon. So regular hexagon, this length will be equal to this. It forms a equilateral triangle. If I draw another line here, it forms a equilateral triangle. 6 equilateral triangles. Okay. And side is 14 centimeters. So area of regular hexagon equal to 6 into root 3 by 4 a square. Okay. A is the side, one side, that is 14 here. So with that you will get this is the area of the hexagon. If you subtract, what you will get is this is the area you want to paint. And what is the area rate at which you are painting? 5 rupees per square feet. So into 5 you do. This is the amount required for painting this shaded area. Okay. Hope you understand it. Let's do exercise 9.3. Okay. In a circle of radius 10 centimeters, a card subtends a right angle at a center. Find the area of the corresponding minor and major segments. Okay. Let's see the diagram first. Okay. Yeah. Diagram is here. Okay. AB is the card which subtends a right angle at the center, and these two are radius, so they will be 10 and 10. Okay. From the given data. And we need to find area of AXB and AYB. Okay. This is nothing but take the sector AOBX. AOBX is nothing but 90 degrees, right? So 90 by 360 into pi r square, that is 25 by 5 pi. And triangle area, since it is a right angle triangle, 10 into 10 by 2, that is 50. So area of minor segment is 25 pi minus 50, which is 28.54 centimeter square. Okay, area of major segment is pi r square minus this minor segment, right? Pi r square minus this, which is nothing but 75 pi plus 50, which is 285.61 centimeter square. Next. In a circle of radius 12 centimeters, a card subtended at an angle of 120 degrees at the center. Find the area of corresponding minor segment. Okay. So let's check the diagram first. Okay, this is a circle. and we need to find AXB. Okay, AXB. Okay. Now, first thing is we need is sector area minus triangle area. Correct? Sector area is simple. First, let's find the triangle area. OC is a perpendicular. OC is the perpendicular. So it will divide this AOB into two equal parts. Now let's concentrate only on one triangle. So this will be 60 degrees because angle also is bisected. OC bisects because it's a isosceles triangle. Correct? AOB is a isosceles triangle. So once this, you know that this is 60, cos 60 is equal to OC by OA. Correct? So OC by 12 is equal to cos 60, which is equal to half, which means OC is 6. You have OC value, you have OA value. So AC is equal to AC square equal to 12 square minus 6 square, which is implies AC is nothing but 6 square root of 3. AC is 6 square root of 3. So area of AOB equal to 2 times area of AOC, which is 6 into 6 square root 3, which is 36 square root 3. Okay. Now area of sector is 120 by 360 into pi r square. That is nothing but 48 pi. So area of minor segment is area of sector minus area of the triangle, which is so 48 pi minus 36 square root of 3. If you calculate, you will get 88.443 square centimeters. Okay. Next. A car has two wipers which do not overlap. Okay, each wiper has a blade of length 25 centimeters sweeping through an angle of 115 degrees. Find the total area cleaned at each sweep of the blade. Okay, angle of the sector of circle made by the wiper is 115. Okay, radius of the wiper is 25 centimeters. Area of the sector making an angle theta is this is the area theta by 360 into pi r square. Correct. Area of the sector made by the wiper is 115 by 115 by 360 into pi r square. Okay, which is nothing but this value. Area total area cleaned by each wiper because you have two blades, right? Is double. So which is nothing but 1254 1254.96 centimeters square. Okay. Next. Find the area of the shaded region in the adjacent figure where ABCD is a square of sides 10 centimeters and semicircles are drawn with each side of the square as diameter. Okay. So AD is the diameter of this semicircle. Okay. AB is diameter of this semicircle and so on. Okay. Now we need to find this shaded area. It looks complicated, but you do this. Area of shaded part can be divided as this way, right? I want to divide it at this point and draw a perpendicular line, so it will become a if you see here we have a quarter circle here, right? You have a quarter circle where the radius, the angle of this sector is 90 degrees. Okay, so you will find the sector area minus this triangle. If you do, you get only this shaded part. Correct? Half of this one leaf, half of one leaf you will get. So four leaves is 8 times basically. Correct? So that's what we will do it. If you look at here, we are trying to find only this half of the leaf, half of one leaf. Okay. So how do you find it? Area of the segment is pi r square by 4. That is quarter circle. Correct? Or you can apply 90 by 360 into pi r square, which is same, minus area of the triangle. Okay, so pi r square by 4 minus pi r square by 4 minus area of the triangle is 5 into 5 by 2. Okay, that is 25 by 2. If you simplify, you will get 7.14 square centimeter. So the area of complete shaded area is 8 times this value. That is 57.12 centimeters square. Next. Okay. Find the area of the shaded region in the figure if ABCD is a square of side 7 centimeters and APD and BPC are the semicircles. Okay, this is very easy. First find the square area, subtract two semicircles. Two semicircles will be equal to one circle area, correct? So very simple. Area of the square minus 2 into area of semicircles. So 7 square because side is 7, which is 49, and area of both semicircles is pi r square, which is nothing but 38.5. So if I subtract 49 minus 38.5, which is 10.5 centimeter square is the answer. Next, in the adjacent figure OABC, OACB, okay, a quadrant of circle with center O and radius 3.5. If OD equal to 2 centimeters, find the area of the shaded region. This is easy. You have a quarter circle first. Okay, you have a quarter circle minus this triangle area. That's all you have to do, right? Area of a quarter circle minus area of triangle. Area of quarter circle is nothing but pi r square by 4, which is equal to 9.625. And area of the triangle is half into 2 into 3.5, which is 3.5. So area of shaded area is 9.625 minus 3.5, which is 6.125 centimeters square. Next. AB and CD are respectively arcs of two concentric circles of radii 21 and 7. Okay, with center O. If angle AOB equal to 30, find the area of the shaded region. So let's see the diagram first. Okay, this is the diagram. 7 and 21. This is very easy. You have two circles, right? So two sectors. Okay, the shaded part is basically area of bigger sector minus area of small sector, correct? Which is 30 degrees because it is given as 30 degrees angle AOB. So 30 by 360 into pi capital R square minus small r square. Okay, so if you simplify, you will get 102.67 centimeter square. Okay, next. Okay, this is same as question 4, where you have single leaf here. Okay, you will find it exactly same way. You have a quarter circle. Okay, cut it. You will get half, then double, twice of that, right? Because you are getting half of the leaf area, correct? So exactly same. Shaded area is twice the area of quarter circle minus area of the triangle. Area of the quarter circle is pi r square by 4, which is 550 by 7. Area of triangle is 50. So area of shaded area is twice the 550 by 7 minus 50, which is nothing but 57.14 centimeters square. Next, let's do some optional exercise. Prove that the angle between the two tangents drawn from the external point to a circle is supplementary to the angle subtended by the line segments joining the points of the contacts to the center. Okay, so this we have done actually already, but let's do. Angle between two tangent line is angle APB, correct? Angle subtended by the chord AB at the center is angle AOB. Okay, it's telling these two are supplementary, means sum of these two angles is 180 degrees. Okay, which is very easy because this is a 90 degrees here, correct? Radius with the tangent, 90 degrees here, radius with tangent. So these two are 180 degrees. Now in this quadrilateral, okay, in this quadrilateral, other two angles should be 360 minus 180. So other two angles are nothing but these two angles, which we are looking at, angle APB and angle AOB, right? So that's very simple. Next. PQ is a chord of length 8 centimeters of a circle of radius 5 centimeters. The tangent at P and Q intersect at a point T. Okay, find the length of TP. Let's go to the figure first. Okay, yeah, this is the figure. So find the length of TP. Okay, tangent length we have to find basically. So this is very easy. We know that yeah, we have solved these problems in the initial exercise itself. Okay, let R be the intersection point here. Okay, let R is the intersection point here. Okay, now OT and PQ, OT and PQ intersection point is R here. Okay, now you know that TP equal to TQ. TP equal to TQ. Correct, we know. So that means these two angles also same. PTR equal to QTR. Okay. These angles also equal. Okay. TR is perpendicular to PQ. Yes. And TR bisects PQ. That is also right. Okay. Therefore, PR equal to RQ. PR equal to RQ. Yes. Okay. Which is 4 centimeters because the total is 8 centimeters. So there is 4 centimeters here, 5 centimeters here. So OR we can get as 3 centimeters. Okay. Once you have the OR in TRP, okay, TP square equal to TR square plus PR square. Okay. TP square equal to TR square plus PR square. Okay. And TP square minus TR square equal to 16. Okay. This is first equation. And in the right angle OPT, this is a big right angle triangle. Okay. In this right angle triangle, you know, this is 5 centimeters. Okay. And there is some value here which we calculated before. In this right angle triangle, TP square plus OP square equal to OT square. So TP square plus 5 square equal to OT is nothing but TR plus 3 whole square. So from this one we get another equation TP square minus TR square equal to 6 times TR minus 16. From these two equations if you look at, okay, TR equal to 32 by 6, 32 by 6 which is 16 by 3. Okay, TR is 16 by 3. That is TR. Okay, now we know TP equal to TR square is equal to 16 square plus this value, so 400 by 9. So TP you will get as 6.67. Sorry, this is TP square, not TR square. We are looking at TP, right? So let me correct it. TP. This is TP. Here we already got as 16 by 3, right? So TP square equal to this value and TP is nothing but 6.67 to centimeters. Okay. Yeah. Next. Prove that opposite sides of quadrilateral circumscribing a circle subtend supplementary angles at the center of the circle. Okay. Yeah. This looks so many angles involved, but most of them are equal actually. So it's very easy. ABCD is a quadrilateral. Draw the radius at tangents as shown. Okay. So we are drawing S R Q P. Okay. P Q R S radius we have drawn. Okay. Now you will get 8 angles as shown here. 1, 2, 3, 4, 5, 6, 7, 8. Consider triangles POB, okay, this triangle, and QOB, this triangle. Okay. In these two triangles, this is 90 degrees, 90 degrees. You have a common side, correct? And you have another common side because this is the tangent from same point. So this BP equal to BQ, correct? And this is radius. All three sides are same. So these two are congruent triangles. Which one is POB and BOQ? These two are congruent triangles. Okay. Once you know that these two are congruent triangles, these two angles are same. 3 equal to 4. Similarly, 5 equal to 6. 7 equal to 8. 1 equal to 2. So once you know all these things, you can play with it very easily. Okay. So half of those angles basically uh, they're pair of equal angles, right? So if I make it, then for 2 times angle 2 plus angle 3 plus angle 6 plus angle 7. Angle 2 plus angle 3, angle 6 plus 7 equal to 360. So 2 plus 3 plus 6 plus 7 is 180 degrees, correct? Similarly, we can prove other two. They are supplementary, that means, right? These two are supplementary. Next. Draw a line segment AB of length 8 centimeters, taking A as center. Okay, this is a problem for construction actually. Okay, first you have drawn AB, then some circle here, then other circle here with 4 centimeters. Okay, draw another circle with radius 3 centimeters. This is 8 centimeters line. This is 4 centimeters radius. This is 3 centimeters radius. Okay, this is approximately, let's assume this is 1 centimeter gap between them. Okay, and construct tangents from each one. Okay, you know how to do this. You take the midpoint of this one, draw a circle. It will cut into 2 points here, 2 points here. Those are the tangents basically. It will go through these 4 points. Okay, so that is how we will do. It looks like that basically. You can do it yourself. It looks like this. You can do it yourself. Okay, this is also another construction thing. Okay, ABC is the right angle triangle with AB equal to 6 and 8. 6 and 8. Okay, and B is 90 degrees. BD is a perpendicular from B onto AC, like this we will construct. Okay, circle should be drawn through BCD. Okay, BCD, a circle should be drawn like this. Okay, so how do you do? This is also 90 degrees. So take the midpoint of this line and you can draw it. Okay, because it's a right angle triangle, circumcenter will be midpoint of this hypotenuse. Okay, you can draw it, construct it. It comes like this, something like this. Okay, and the tangent from A to this circle. Okay, next. Find the area of shaded region in the figure. This is very easy. You have a bigger circle, you have a smaller circle. Bigger circle minus small circle, you will get it. Right? Very easy. Pi r square minus r square, pi 8 square minus 3 square. That is nothing but 172.85 is what you will get if you calculate it. Okay, next. Yeah, this one also, if you look at, you can cut into one semicircle here, one semicircle. So one full circle, two small semicircles, then one rectangle area, then minus this semicircle. Okay, so put the values properly, you will get it. Area of two small semicircles is pi r square, which is 28.5. Area of rectangle is 14 into 7, 98. Area of big semicircle is half into pi r square, which is 77. So you just calculate the shaded area. It will come around 48.5 centimeters square. Thank you. Yeah, that's all about the tangents and secants. It looks very simple, but remember this because you are going to look at geometry as a whole, not as individual chapters, right? So each theorem and statement given here, everything is useful in some other geometry. Okay, like how we are using Pythagoras theorem in this, and how we are using isosceles triangle rules here, equilateral triangle rules here. Correct? All those things are not studied in this chapter, right? But we are using them. Similarly, whatever you studied in this tangents and secants, you will be using in other area, okay, and other geometry and other lessons. Okay, so that way it is very important. But if you look at you, it is a very precise and small chapter with few theorems, and most of them are very intuitive. By looking at, you can tell, okay, this theorem can be easily proved, right? So hope this is good. We'll come up with more chapters, more 10th class chapters. Thank you.